Hello everyone. In this video, we are going to discuss about the ripple carry adder. See, actually, in the previous video, I had discussed about the half adder circuit. Half adder circuit is used to add two single bit number. But when you want to add a binary string, then the half adder won't be suitable. We have to use a full adder circuit. So in this video, we are going to see how to use a full adder circuit to design the ripple carry adder. So we'll see how we can design a 4-bit ripple carry adder. So that means I'm going to add two 4-bit number. So that is why I'm saying that as a 4-bit ripple carry adder. So when you wanted to perform an addition process, so we have to start the addition process from the LSB of the organ and the addend. So LSB in the sense, see for example, when I take this number, okay, so here I have two binary string. This is organ, this is addend. So this is the LSB of the organ and this is the LSB of the addend. So always you have to start the addition process from the LSB until you reach the MSB of the binary string. So this is how an addition process will be performed. Okay. So we'll see how we can perform the addition on a 4-bit number. So I'm naming A as A0, A1, A2, A3 and similarly uh, binary string of B as B0, B1, B2, B3. So this is the LSB of augment and addend. So you want to start the addition on LSB. So A0 is equal to 0, B0 is equal to 0. So when you add 1 plus 1, the result is equal to 2. The binary equivalent for 2 is equal to 0, 1. So I'm placing 0 in the sum and I'm taking the carry to the next position. That means I'm rippling the carry to the next position. That's why it's called as the ripple carry adder, or else you can call that as a propagating the carry to the next position. So here I got carry as 1, so I'm rippling the carry to the next position. So here carry is equal to 1, A1 is equal to 1 and B1 is equal to 0. So 1 plus 1 plus 0 is equal to 2 again. So I'm placing 0 here and taking the carry to the next position. Here C2 is equal to 1, A2 is equal to 0 and B2 is equal to 1. So 2 again, so 0 and then I'm taking carry to the next position. Here in this position C3 is equal to 1, A3 is equal to 1, B3 is equal to 1. So the decimal equivalent of this bit addition is equal to 3. Binary equivalent of value 3 is equal to 1, 1. So we got the final result as 1, 1, 0, 0, 0. But here we are adding two 4-bit number. So the result should be 4-bit only. But I got a 5-bit number. So the last bit should be ignored. So this is how we have to perform the addition process. Next, see, actually, we have witnessed that the previous bit position is, previous example, we have added at each bit position, we have added 3 bits. So when it comes to the LSB or the first bit position, so we have only A0 and B0. So we have to take carry in C0 as 0. Okay. But for the remaining position onwards, we'll be getting a carries from the previous position and that will be added along with that. But for the first bit position, we don't have a carry. So we have to take C0 is equal to 0. So that is how this ripple carry adder addition will be performed. Okay. So when you look at this example, we'll be adding 3 bits at each bit position. So that means we can clearly say that half-adder circuit does not suit for this because half-adder will add only 2 bit at a time. Okay, but here we are adding 3 bit at each and every position. So we need a full adder circuit. So full adder circuit is actually a combination circuits. So that perform addition on 3 bit number. Okay, so 3 bits are organ, addend and carry in. So after adding organ, addend and carry in, it will be producing two outputs, sum and carry. Okay, so the sum will be retained for the result and carry will be propagated for the next position. So by using 4 full adder circuit, I have designed a 4-bit ripple carry adder. So the input for the first bit, first ripple carrier is A naught, B naught, and C naught. C naught will be considered as 0 always. So after adding A naught, B naught, and C naught, so it will produce sum, and if there is any carry, so that will be propagated to the next position. So the next position, so second full adder will add A1, B1, and C1. Then it will produce one sum and carry. Carry will be propagated to the next position until we reach the MSB of the binary number. So when you get carry out, that means the carry for the last bit question, so that will be ignored. Okay, so this is the second example. So here I'm going to take A is equal to 5 and B is equal to 10. So A is the organ and B is the addend. So I'm going to add this one and as I said, like C should be considered 0. So C naught is equal to 0, A naught is equal to 1, B naught is equal to 0. So the result is 1. So sum is equal to 1. There is no carry. So carry is equal to 0. So C1 for the second bit question is equal to 0. So 0 plus 0 plus 1. So sum is equal to 1. So here again there is no carry. So C2 is equal to 0. C2 is equal to 0. A2 is equal to 1. B2 is equal to 0. So sum is equal to 1. And the carry is 0. So carry will be equal to the next question. So here again C3 is equal to 0. A3 is equal to 0. B3 is equal to 1. So 0 plus 0 plus 1 is equal to 1. So result is equal to 1, 1, 1. So here we didn't get the carry out. So you no need to do anything on that. So this is the final result. 1, 1, 1, 1 is the final result. Okay, so this is how a ripple carry adder will be performed as shown in this diagram. So we need to take 4 full adder circuit for performing addition on 4-bit number. Okay, so in order to design a 4-bit ripple carry adder circuit, so first we have to take a 1-bit full adder, then we have to connect the 4 1-bit full adder to get the 4-bit adder. Okay, so we know how to design the 1-bit full adder circuit that we had discussed in the previous video. Okay, so the actual procedure to design the full adder circuit is you have to draw the truth table. So truth table will take 3 inputs A, B, C, and it reproduces 2 outputs, sum and carry. And after completing this truth table, you have to derive the expression. From the expression, you have to draw the circuit. So this is the circuit design for a full adder circuit. So since we are going to design a 4-bit ripple carry adder, we need 4 full adder circuit. So first full adder takes A naught, B naught, and C naught. It produces S naught and C1, and C1 will be rippled to the next position. So the next full adder will take B1, A1, and C1 as the input, and it produces C2 and S1. C2 will be rippled to the next position until we reach the MSB of the number. So this is how a ripple carry adder will be designed, and the ripple carry adder will be used to perform addition on augment and addend. I hope you all understood the concept. Thanks for watching. Thank you.